The next factor that will affect the landing performance is the wind. Shown here is a landing with no wind in order to create a comparison example. You will recall that headwinds decrease the true ground speed of the aeroplane for any given indicated airspeed. Thus, during a headwind, the forward speed over the landing surface is much less, and as a result, the distance required to bring the aeroplane to rest is decreased. A tailwind will have the opposite effect, and it will increase the ground speed for a given indicated airspeed. Thus, during a tailwind, the forward speed over the landing surface is much greater, and as a result, the distance required to bring the aeroplane to rest is increased. When examining the effects that winds have on landing performance, it is recommended that you do not use the actual wind that is given, just in case the wind changes to a worse condition than the one you have planned for. When calculating actual landing distances, it is recommended that you assume only 50% of the headwind component and 150% of the tailwind component. Most performance graphs that calculate the landing distance have the 50% headwind and 150% tailwind recommendation already applied. The example shown here demonstrates this. An important note is that there is no allowance for crosswinds, and therefore no safety factor for crosswinds. Crosswinds present an additional complication because of the effect of potentially crossed controls, which would have to be applied because the wind will tend to push the aeroplane off the centre line. These issues mean that aeroplanes are given maximum crosswind limits. The next factor that can affect the landing performance is the slope of the runway. Slope has an impact on the landing distance because of its effect on how the component of weight acts along the longitudinal axis of the aeroplane. When the aircraft is on an upslope, the weight still acts towards the centre of the Earth, but there is a component of weight, shown here, which acts in the direction of drag, that is, backwards along the longitudinal axis. This will increase the deceleration of the aeroplane and therefore decrease the landing distance. Conversely, when the aeroplane is on a downslope, the weight component now acts in the direction of thrust. This adds to the forward force, therefore it will decrease the deceleration and increase the landing distance. A rough calculation to help quickly quantify the effect of slope is to assume that for every 1% slope, the landing distance is affected by 5%, or a factor of 1.05. The slope at some airfields means that the landing may only be possible in one direction. These are called unidirectional runways. Treat these runways with extra caution and always check that the current wind velocity will still allow a safe landing, since you may be forced to land with a tailwind. Although it will be made clear later, the landing regulations state that upslopes are not to be considered when calculating the landing distance, since upslopes will help to reduce the landing distance. Most landing performance graphs assume a paved hard surface. If the condition of the runway is not like this, then the effect on the landing distance needs to be understood and corrections applied. A lot of small airfields have grass runways. The grass will increase the drag on the wheels. However, grass severely reduces the wheel friction to the runway compared to a paved runway, and therefore the wheel cannot be retarded efficiently by the brakes. Otherwise, the wheel will lock and the wheel friction with the runway will reduce even further. The overall effect is that grass runways will increase the landing distance. In light general aviation aeroplanes, this increase in landing distance is about 15% compared to a landing on a paved surface. However, most landings that you will carry out throughout your professional career will undoubtedly be on hard paved runways. If the runway is covered partially or fully by contaminants such as standing water, snow, slush or ice, then pay special attention to effects that they will have on the landing distance. These substances will have two main effects. The first effect is that they will create impingement drag. But more importantly, the second effect is that these substances will substantially reduce the friction between the wheel and the runway. Therefore, the wheel cannot be retarded efficiently by the brakes. The graph clearly shows that as a result of the reduced friction, and therefore the subsequent reduced braking action, any contamination of the runway due to water, snow, slush or ice will significantly increase the landing distance. This table shows the deceleration of an aeroplane during the landing based on different surfaces. You can see the large reduction in deceleration on icy runways. Typically, on a dry runway, the braking coefficient of friction is between 0.8 to 1. But on wet, slippery or icy runways, the braking coefficient of friction can fall to less than 0.2. Shown to the left and right of the runway friction values are the runway terminology and ATC friction reports. These help to provide aircrew with more information about the conditions for landing. Because of the lack of effective braking on slippery surfaces, the aerodynamic drag and reverse thrust become much more important in bringing the aeroplane to a stop, as shown in the diagram to the right. Notice that on flooded or icy runways, reverse thrust accounts for 80% of the deceleration force, confirming its importance as a deceleration tool. Next, you'll hear a commentary from a Canadian air traffic controller about a situation when the runway was slippery.
We had some freezing drizzle fall while the temperature remained near freezing. This left an ice-covered runway. The Dash 8s didn't say anything about braking action. Then a BAE 146 landed. I watched him drop off the radar and gave him several seconds to get slowed down. I told him to take the first available right turn and report off the runway on my frequency, so the Boeing 757 behind him could get a landing clearance. He responded saying,
"Well, we're still sliding here. We'll let you know when we get stopped."
After what seemed like an eternity, a shaken voice came over the radio.
"We're just getting it stopped now, about 75 feet from the end of the runway. We'll call the braking action nil."
I reported this to the 757, anticipating that he may not want to land. He asked for a landing clearance, which I gave him. Upon landing, the 757 reported braking action fair and turned onto a taxiway about 1,500 feet from the end of the runway, without a hint of panic in the voice. What a difference thrust reversers can make.
This part of the lesson is interactive, and it will help you to understand the relationship between the various types of contaminations, the braking effect with these contaminations, and the effect on the stopping distance. The aeroplane is travelling from left to right. You can select the type of surface you want to use, either dry, wet or icy. Once you have done so, looking to the left hand of the screen, move the slider on the horizontal bar underneath the 3 gauges. Moving the slider to the right increases the applied brake force. Be careful though, too much braking force will cause the wheels to lock, and this will change depending on the runway contamination. When you have completed this section, click on the forward arrow to continue with the lesson. An important point to note is that there is a distinction between the definitions of a damp, wet, or contaminated runway. A runway is considered to be damp when there is moisture present on the surface which changes its colour, but insufficient moisture to produce a reflective surface. A wet runway is one whose moisture level makes the runway appear reflective, but there are no areas of standing water in excess of 3 mm deep. Wet runways can cause the average dry landing distance to increase by as much as 50%. A contaminated runway is one where more than 25% of the runway is covered in a layer of moisture whose specific gravity is equivalent to a depth of 3 mm or more of water. The importance of runway contamination cannot be stressed enough, as many fatal accidents may have been avoided had due account been taken of the situation. From what you have learnt so far, it is vital that the pilot be aware of the type of runway contamination, its depth, its extent, its effect on the braking, and of course its overall effect on the operation concerned, in this case the landing. The information on the runway contamination and braking effect can be given to the pilot through a report. These reports are either by SNOTAM, Runway State Code, PIREPS, or spoken by Air Traffic Control. These reports may include braking action or braking coefficient. Use any runway report together with your aeroplane flight manual and standard operating procedure to best gauge the landing technique and landing performance. The second type of hydroplaning is called viscous hydroplaning. It occurs because of the viscous properties of water acting like a lubricant. A thin film of fluid not more than 1/1000th of an inch deep cannot be penetrated by the tyre in the footprint area, and the tyre rolls on top of the film. Viscous hydroplaning can occur at a much lower speed than dynamic hydroplaning, but it requires a smooth surface. The most positive method of preventing this type of hydroplaning is to provide a microtexture to the pavement surface which breaks up the film of water, allowing it to collect into very small pockets. This means that the tyre footprint will sit on the peaks of the textured surface as shown, and not the film of water. Reverted rubber hydroplaning is a complex phenomenon which over the years has been the subject of a variety of explanations. Reverted rubber hydroplaning requires a prolonged, locked wheel skid, reverted rubber, and a wet runway surface. The locked wheels create enough heat to vaporize the underlying water film, forming a cushion of steam that lifts the tyre off the runway and eliminates tyre-to-surface contact. The steam heat reverts the rubber to a black gummy deposit on the runway. Once started, reverted rubber skidding will persist down to very low speeds, virtually until the aircraft comes to rest. During the skid, there is no steering capability and the braking effect is almost nil. Reverted rubber hydroplaning is greatly reduced in modern aeroplanes due to the standardization of advanced anti-skid braking systems, which prevent wheel lock-up. This section will provide advice and guidance on how to land on contaminated runways. Firstly, check the current weather and the runway conditions using the most accurate information possible. Once this has been done, completely reassess the landing performance data to ensure satisfactory compliance to the regulations. Ensure you're at VREF at the landing screen height and prepare to land the aircraft in the touchdown zone within the 1,000 feet target of the airborne segment. Land on the centre line with minimal lateral drift and without excess speed. Arm auto spoilers and auto brakes as appropriate, which assure prompt stopping effort after touchdown. For aeroplanes fitted with automatic anti-skid brakes, the brakes will be applied above the dynamic hydroplaning speed, but for aeroplanes without this system, only apply the brakes below the dynamic hydroplaning speed. The flare should lead to a firm touchdown, sometimes described as flying the aeroplane onto the runway. Positive landings will help place load on the wheels, which will increase braking effectiveness and squeeze out the water from the tyre footprint area. Do not allow the aeroplane to float, and do not attempt to achieve a perfectly smooth touchdown. An extended flare will extend the touchdown point. Soft touchdowns will delay wheel spin-up and delay oleo compression, which is needed for auto brake and auto spoiler activation. After main gear touchdown, do not hold the nose wheel off the runway. Smoothly fly the nose wheel onto the runway by relaxing aft control column pressure. Raise spoilers as soon as possible after touchdown or confirm auto spoiler deployment. If the aeroplane does not have auto brakes, then initiate braking once spoilers have been raised and nose wheel has contacted the runway. Apply brakes smoothly and symmetrically. Initiate reverse thrust as soon as possible after touchdown of the main wheels and target the rollout to stop well short of the end of the runway. Leave a margin for unexpectedly low friction due to wet rubber deposits or hydroplaning.